So in our first unit in the introduction of functions, we mostly looked at linear functions. Not every time, but mostly. So let's look at some of those again. Remember the party problem. So in 1 hour, one person, 2 hours, four people, etc. Some of them were upside down, some of them were right side up, but our function was just talking about trying to describe how many total people there were. So when x was 1, y was 1. In other words, when after hour 1 there was one person. And we could graph that point 1, 1. We could do the same after 2 hours when there were 4 people. 3 hours there were 7 people. And we could keep going. 4 hours there were 11 people. So we could graph all those points if we wanted to. And we don't really know, is this a linear function? It looks like it. Those points look like they form a line. Not sure. How else could we explore this? Well, we could look at the growth, and we can see that y is growing by 3 when x goes up by 1, and that keeps happening, so we have a constant growth of plus 3 when x goes up by 1. We could find the function as an equation. We could write the equation as f of x equals 3x minus 2. That's one of the many possible equations you may have come up with. And if you know anything about what the equation of a line looks like, we can say that this is linear. We know that constant growth is linear. And we know that if the graph looks like a line, it's linear. So we could go ahead and use a dashed line to connect those points. We use a dashed line because we know the points shouldn't really be connected. This is a discrete function. Half a person doesn't make sense. So we use a dashed line to show what's going on here in the relationship without saying that we have to connect the lines. This indeed is linear. We have a straight line. But remember Fernando. Fernando came up with this function as an equation when trying to describe how many total tiles there were. And we can explore this with a table as well, right? We have when in the first figure there were 5 total tiles, and we could graph that. 1, 5. We could do the second figure had 10. Third figure had 17. The fourth figure, which wasn't really drawn, had 26. And that one's a little harder. Do those points line up to make a line? It's kind of hard to tell. We have the equation. It doesn't really look like the equation of a line. We could find the growth. I'm not going to do that right now, but you could try to do that. Why don't we just try to graph a few more points? Now, it doesn't make sense to say negative figures, but we could go ahead and graph them anyway, knowing that it doesn't make sense in this problem, but it helps us explore the relationship. So let's put in there when x is 0, negative 1, negative 2, and negative 3. Whoa, that definitely does not make a line. And if we use the dashed line again, we can see definitely not a line. This is not linear. In fact, it's quadratic. That's a parabola. Some of you may have already known that. Some of you may not have. That's okay. We'll get there. The whole point that we want to get across here is just that it's not linear. Let's look at another example. We have triangle 1, triangle 2, and triangle 3. And each triangle has its own area. Let's try to find a function to model that area. So we have in triangle 1, the area was 1. How do I know that? Because I can do base times height divided by 2. 1 times 2 divided by 2. For triangle 2, I know the area is 3 because, again, I can do base times height divided by 2. 2 times 3 divided by 2. The same thing for the third triangle. And the fourth triangle, which isn't there, I know it's going to be 4 times 5 divided by 2, which gets me 10. I can do the same thing for the 100th triangle. 100 times 101 divided by 2, which gets me 5,050. For triangle T, A of T would be T times T plus 1 divided by 2. Again, I could graph this if I wanted to. I could use the dashed lines if I wanted to. And I can see that it's not a line. It's not linear. So not all functions are linear, and we're going to start exploring this idea in this next unit.